Good morning, folks. Brent Jeffries, Vice President of Field Operations with Bierer Meters, and we're coming today with a special presentation. Mr. Dan Taylor with ISPC, the Institute for Safety in Powerline Construction. He's going to be sharing changes in personal protective grounding with you all today. Today is going to kick off our anniversary of Electric Culture of Safety. It's 1 year. Basically, this month, Danny Rains kicked it off with the 002 electric system grounding. So this is 1 year. So now we have over 5,000 registered members to Electric Culture of Safety. And these videos are going out to our line crews, our line team, nationwide, into Canada, a little bit overseas. And this is all at no cost. The ISPC is actually sponsoring today by sending Mr. Dan Taylor out here to speak with you all. So this is really a neat day. And just real quick, we've got right here, we got Mr. Rod Courtney. He's coming back. He was with us this last July of 2022, and he spoke about the 8 habits of an effective, highly effective safety culture. And his book that just came out in July when he spoke is now #1. So he's coming back. So the #1 bookman, Mr. Rod Courtney with Empirical, he's coming back next month. And he's got another speech to share. It's going to be called Tip of the Spear, a tactical approach to safety leadership. So excited about that. And then in April, we're going to have Mr. Mark Todd. He's a good friend of mine. Been working with the Electric Cities of North Carolina for a few years now with their safety program, sharing some of our tools with them. And so they're on board, and they're going to be sponsoring in April. So I've known Mr. Dan Taylor. I met him at the IP conference this last, when was that, Dan? November, yeah. And we had a good discussion, and the ISPC, that group, they basically are supplementing and they're partnering up with ECOS, and this year they themselves will be sponsoring 8 different subject matters, bringing 7 different folks in to share, actually 6. Jimmy Vaughn will be twice, and Mr. Mac Turner, he'll be sharing twice this year. So these videos, register. Just all you got to do is go to safetytraining@biermeters.com, email me, you register, and then you will receive all the live line links, you'll receive all the videos, all the recordings, where it should be up to 2 every single month starting in May. So 2 Linemen Safety National Webinars a month. And those are all at no cost. These folks are giving back. These companies are sending their folks in and giving back to you all for no cost. So with that, we'll go ahead and introduce Mr. Dan Taylor.
Today I want to talk a little bit about the changes in grounding as far as when I started off. So anyway, protective grounding, the limits of the zone. So what are the things that we don't know? This is Jim Vaughn's slide that maybe a lot of you have seen. As you all know, some things that we don't know and the things that we don't know can hurt us. And hopefully today, as we talk about things, hopefully I can bring some awareness to you of maybe different paths or something that we didn't think about. I know that when I was going through that as far as an apprentice, a lineman, line foreman in my career, some of the paths I never thought about. When I went to do a grounding, I never maybe took that time to look and see how the actual paths, and hopefully today we'll talk about some of them, and maybe you can realize some of the things that you do day to day that may be similar or the same. So let's talk a little bit about misunderstandings. And I know that Danny Rains had a slide a whole lot like this a year ago. So what are some of the misunderstandings of grounding? Okay, what's the first thing? We ground so we don't get electrocuted. That's kind of what we've been taught all our life. Okay, if I ground it, I'm going to protect myself. If I ground it, it can't get hot. It cannot become hot. What about people on the truck? People around the truck. So if I ground it, are they safe? Some things, you know, as that we was kind of taught years and years ago that we didn't understand maybe. What about the public as they're coming by? So we're going to talk about that quite a bit today. So grounding, very misleading, okay? And it's used incorrectly across the thing. The reason is grounding does not ensure protection of the workers. Does not ensure protection of the workers. Okay, grounding principles. Okay, principle number 1. Current flows in every available path inversely proportional to the resistance in the path. And we're going to talk about all 3 of these individually as we get to them. Number 2, if you insert a resistance in a current carrying grounded conductor, a voltage rise will appear and the voltage will be proportional to the resistance in the path. Number 3, it takes 50 volts to break the electrical resistance of your skin. So if voltage breaks that resistance, current can flow and you can become injured. Okay, according to OSHA and ANSI and IEEE, here's 2 narrowly defined definitions. Number 1, cause immediately operation of protective devices in case of accidental energizing of lines. Number 2, shall be arranged to prevent each employee from being exposed to hazardous differences in electrical potential. So what are we actually talking about here? We're talking about grounding. And we're talking about bonding. Okay? So we ground for one purpose, we bond for one purpose. So before we begin, first thing we want to remember, what is the purpose of grounding? Second thing, what is the purpose of bonding? Okay, here's principle number 1. So, current flows in every available path. Okay, so as thinking back as you started career, maybe some of you started a long time ago like I did, I was taught a certain way to ground, and then I never questioned it. I just thought, well, if I ground this way, I'm going to be safe. But you can see the different paths. It's going to take every single path to ground. Okay, here's a distribution line. Follow the curves. Now you can see every path, every ground wire, every pole bond. We're going to have current flowing through every single one of them. Every available path. Maybe this one over here has the most. Maybe this one over here has less. Maybe this one has more. Just depends on what kind of connection that we have. So every available path. Okay, so number 1, what's the number 1 purpose that we ground the system? We want to cause immediately clearing for those dangerous faults. And we provide a low impedance path to ground. Okay, so that's what we're grounding for. We want to open that recloser just as quick as we can. So, real value of bracket grounds. So we have our work location. We got our putting up our working grounds here. So we have our pole bond. We have a ground here. Okay, we have the ground, the pole bond going down the pole. Now we'll set up our bracket grounds. If this becomes energized, we're going to divide the path. We're going to divide that current into 3 locations. So now we've took that current, we divided it into 3, so now we just have to control a smaller amount. Okay, so now let's talk about the touch potential. Since we're right here by the truck, whether it's a truck, whether it's a pole, whatever it is, no matter if that truck's grounded, if we touch, we still make that path to ground. Even if maybe we're not touching a truck, we still have a step potential here that we have to be thinking about, understanding. Here's our step potential. See, if we have 1,000 volts here, you can see how the more further away we go out here to 10 feet, where it drops off to pretty well 0. So what are we actually measuring here from one to the other? Okay, we have potential difference between here and here, or the gradient. So here's a pretty, we have a ground rod right here. We can see this quite easily. If this becomes energized, you can see how as far as it gets away from this ground, you can see where this 10-foot rule that we talk about, 10-foot rule. You can see where it kind of dies out to no voltage here at 10, but you can see how much more powerful it is here, how higher it, and then the further we go, a little bit less and less and less. Okay, here's at the ground rod, 7,200 volts at the ground rod. You can see out here approximately 2 feet as he steps out here 2 to 4, 2 to 6. We have a 1,300 volt difference between one step and the other step. So it's something that we need to think about, that sometimes I know that was one thing as far as myself that maybe I never thought about as much. Okay, number 2. If you insert a resistance in a current carrying grounded conductor, a voltage rise will appear. Okay, and that voltage will be proportional to that resistance in the path. Voltage drop usually refers to voltage change across a resistor in an energized circuit. Should be but isn't, shouldn't be but is. The potential difference is also used to describe voltage across 2 conductors at different voltages. So, think about your system that you have. We have incidental and intentional. So the system, as it's been built and engineered, we have some safety that has been built into the way that it is constructed. And then we go with the intentional, whether it's putting up grounds, whether it's putting up some kind of grid here in a substation. You can see these that they've set on top of this grid to protect them as they're switching, as is common nowadays. So intentional versus incidental. Things that we expect versus things we don't expect. So let's talk about the resistance in a line. So as you all know, if you have a power line and you start at a substation and you have to go approximately, let's just say 50 miles, we know that we have to step the substation up 127 volts So by the time we get down the line, we still have usable voltage because of the resistance in the line. Who here tests your own grounds? Here's an old ground chain tester. For the ones that have tested their grounds, they kind of understand how it works. If you don't test your grounds, I'll give you a pretty quick and easy to go through. So we just take the length of the cable and the gauge of the cable, and then there's a chart here. So as we add the voltage, it has to meet a certain criteria to be able to pass or fail. So depending on what kind of resistance that we have, if it's too high, then we can go through and we can check the clamp. We can check the ferrule, we can check the cable, and we can figure out where the problem is and then fix it and replace it to make it so it is safe for us to use. Test those annually. And we need to take care of them, put them in a certain bag, keep them clean, because when it comes time to actually use those, and I'm going to talk about an incident that happened not very long ago, you can see the importance of the way we take care of things. I'll get to that in just a minute. So, okay. How many's been out on outage? I'm sure every single one of us have. We go out on the outage and we have line that's down. So what is the first thing that we do, that we're told to do? We put a set of grounds up, correct? So now I put my bracket grounds up, like I've been told. What did I just do? I went out, I put my bracket grounds up. What did I just do? Where is my current carrying grounded conductor now? I just put it up here. The only thing I did is just change from moving my neutral from there to up here. So, grounding plays a really important role because we want to open that recloser. We want to get that power, that hazard, away from us just as quick as we can. But the problem is, grounds are not all the same. What are your grounds like? Do you have 2 or 3 different kinds? Have you settled on to one? Is your grounds adequate for the fault current that you have on your systems? A lot of things, you know, we have to think about as far as what our grounds are, the grounds that we use. Okay, so voltage rise. We do know that voltage is going to rise. We have a ground here. Okay, depends on what resistance in the path, how high that's going to be. So I have this set of ground here, this ground that's put on the pole. Okay, now on this ground you can see there's more resistance in this ground than in this ground. Okay, you can see the difference in the voltage between the two just because of the resistance of that ground chain. So, where is the actual hazard here? You're probably okay if you touch this one. Grounded here, you're probably okay here. Where's the problem? It's between them. See the voltage difference between the two grounds? That's where the risk is. So like I said, each phase might be safe to touch, but possibly between them might not be. So you can see the differences in our grounds. So I'm going to ask the question to you again. What is your grounds? Are they different? Have they been tested? How do we make it safe? So if we put a bond between, now the voltage is the same. Now it is safe for me to work between them. What other hazards here? What other hazard occurs here if we set up parallel grounds? We have circulating current. And that is one thing that I didn't think about as much as I probably should have in my career about that circulating current that we create ourselves sometimes. And we're going to talk about some incidents that have happened because of that same principle, something that was there but wasn't realized. Okay, here's a typical distribution. I know that the neutral's up here on top, but it helps us kind of see it a little bit better. So every single structure, we're connected to the bond on the pole. So we have circulating current. Anytime that we have power flowing, we have current flows. We have circulating current flowing all the time. What happens if we lose a ground here? Now our path is just a little bit bigger, but it's still circulating. Principle number 3. It takes at least 50 volts to break the electrical resistance of your skin. If it breaks the resistance of your skin, current can flow, and you can become injured. So if we can keep that below 50 volts, we call it a buffer zone. And we're going to talk about that a little bit more, but we can keep this between 50 volts and 50 milliamps. It's kind of where our buffer zone that we're going to talk quite a bit about today. Okay, what is our equipotential zone? What does OSHA tell us? 1910-269. Equipotential zone. Temporary protective grounds shall be placed in such locations and arranged in such a manner as to prevent an employee from being exposed to hazardous differences in electrical potential. I've heard a lot about people say, what is this new standard? Is this a new standard? I want you to think about that for a few minutes. Okay, so electrical bonding the worker. Okay, it takes advantage of that buffer zone with the potentials. Okay, takes advantage of the buffer with potential that does not exist with current. Okay, so the buffer is what it takes to penetrate the skin. And like I said, if the voltage does not reach that penetration threshold, current can't flow and you can't be hurt. But what happens if current does flow? How much does it take to actually hurt us? What should we be worried about? Should we be worried about tenths, hundredths, thousandths, 10,000ths, 100,000ths? What should we be worried about? How much power does it actually take? Thousandths of an amp. this is what we're going to be talking about. Milliamps. Charles Dalziel, he was the inventor of the GFCI breaker. And he did a bunch of testing, and what is really neat about this, I don't know if it's neat, but he had some volunteers years and years ago, and they was prison inmates from a couple of prisons. And they went through, and they were the ones that actually did these tests. These tests down here is the ones that concern me. Would have been kind of interesting to see the ones that actually figured out where the defib came from. But you can see muscle control loss, 9 milliamps for men, 6 milliamps for women. How many of you have been working on a line and been around, touched something, grabbed something, was at that point to where you could not let go? When I was about probably halfway through my career, we was running a service over in a little town, and I just come from across the road. We had the road blocked off. I hung a wire on one side. I come around to help my pole buddy on the other side, which, you know, back in those days, we was a little bit shorter of crews. We was small in numbers compared to what we have nowadays. Anyway, there was 2 of us on that crew that day. I can remember just getting across the road, and my pole buddy was up a pole, and there was a wire coming down to a street light, and somehow he came in contact with that street light wire that was energized, and he could not let go. And I can remember just hearing him up the pole, and I remember looking up the pole and seeing him contracted and not being able to let go. And so I just took a second to assess the situation, and I just started to head up when he was able to kick his hooks out and drop down, which cleared him loose from the pole. So I've actually seen that, and it's quite scary. It's quite, it was quite interesting at that time. But 16 milliamps, that's not very much power at all, is it? For women, 10 milliamps. Men and women, you can see at 3 seconds, 100 milliamps. What about your lights? How much power do they take? The old light bulbs was about 120 watts, 1 amp of power. So you can see it doesn't take hardly any amount of power at all to do damage to our bodies. And to put our heart into defib or cardiac arrest even. But you can see right here we're talking about, this is probably secondary voltage. You can see it 30 milliamps. If we have a hold of that for 5 seconds, it's the same if we have 300 milliamps for a half a second. There isn't any difference. So, our buffer zone, if we can keep it below 50 milliamps, that's where our buffer zone is. Okay, so the problem's not the current. You see this high resistance, me up the pole. Now I have my low resistance ground here, okay? If that becomes energized, you can see the problem that I have here. So if I put a equipotential bracket on the pole, what did I do to this? What happened here? Now everything's at the same potential, so I don't have this high resistance here. That's gone. My low resistance here takes it around me for my bond phase to the pole. So how long have we been dealing with this? The use of grounds remote to the work location does not ensure protection to the lineman working in contact with conductors supported by either wood or steel structures. So, let me talk about a minute when I started the industry 40 years ago. I think that as line workers that we should ask why. We should understand some of those principles instead of just take it for granted what we're told by our supervisor, our line foreman. So, think back to my career 40 years ago. So, we're always told if it is not dead, if it's not grounded, it's not dead. It's what we've been taught all our life. Okay? So, I was taught to put up bracket grounds. And then if I was working in between, I was safe. At least that's what I assumed. Okay? I didn't ask why. I didn't figure out what the principles were. I didn't understand those. I was told, if I put up my bracket grounds here and here and I work in between them, I'm safe. So, that's what I did all my life. We would ground here, and then I work here. Everything's good. Done it the same way for 30 years. Nothing happened to me. Okay? So, I'd probably been there about 10 years-ish. Somebody comes and they bring in this Equipotential grounding in the 80s. So what do we do as linemen? I've been doing it this way for 30 years. Why should I even... I've been safe. Have I been safe or have I been lucky? So, we're taught how to use Equipotential. In the 90s, we're retaught how to use Equipotential because we're not doing it. We haven't changed. We're still bracket grounding. Why was there emphasis brought back in the 90s? Well, we're killing a lot of people. A lot of people are dying, and so they reintroduce it, I guess. That's what we'd say. Even though it's been there, they bring it back and they reintroduce it. And so what do we do as linemen? We go through and we try it a time or two, and then pretty soon we're out working. Well, we don't have time to monkey with that. So now pretty soon we're back to the same way that we was 40 years ago, 50 years ago. Then it's reintroduced again 10 years later. Then it's reintroduced again in 2017. Okay, so on wood pole construction using a neutral conductor which is periodically grounded, a safety zone may be established near the top of the work structure by a pole band installed below the work area and connected to the neutral and phase conductors. So how long have we been actually knowing and understanding that if we put up bracket grounds, we was not safe? 1955, we knew in 1955 that bracket grounding did not save lives. We knew in 1955 that if we put a safety zone, an Equipotential zone, that would protect the workers in 1955. 2023, how many of us are still bracket grounding? How many of us use Equipotential? I think, we get this all the time at ISPC. We get, what is this new grounding rule that come out? All it was changed and maybe added equipotential into the grounding. So everybody is wondering, having a panic. OSHA is requiring us to use this new rules. Well, it isn't new. It has been there for years and years, but we as an industry have not developed the habits, or we have not understand the principles, or we just do it the way that we've done it for 30 years. Nothing's ever happened, 30 years. So, 50 years ago, this is how we have always done it. So, lineman up a pole. I put my bracket grounds, I have my bracket grounds on each side of me. It becomes energized. What's principle 1? Every available path. Now this might be less here, but is less too much? Obviously, most of the time it is, because of the fatalities that keep occurring. The current's going to flow inversely proportional. Okay? That's how we did it 50 years ago. It's a crapshoot. Every situation is different. Okay, here's how we're supposed to be doing it today. Okay, we have our pole bond on just about every structure we have. Some might be every 3 structures, 4 structures, every 5. Some might be every single pole with a butt plate, ground rod, butt plate, but we have this zone that's pole bond on each pole. Same lineman up the pole. Now, I have my bracket ground, plus I have my equipotential bracket set up here. Okay, now what happens when it becomes energized? You can see my zone that I set up here. So if the pole and the wire are at the same potential, current cannot flow. So if current cannot flow, I'm protected. So, you can see my bond between the pole and the phase. The potential gap is between the phase and the wood pole. The bonding jumper is phase to wood pole. The wood pole limits the amount of current that can flow. The resistance-free bonding jumper eliminates the potential difference between the phase and wood. There, the voltage difference is less than 50 volts. So if we can stay under that buffer zone that we've been talking about, if we can stay below that 50 volts, and the resistance in our skin cannot be penetrated, current cannot flow across the worker. So if we can control the voltage, the current does not matter. Okay, so potential differences. So if I have 7,200 volts and I have an open in that line, and I'm grounded here. And if I put a meter between the two, what am I going to rate? What am I going to read on that meter? 7,200 volts. Okay? Now if I have 7,200 volts, and I have some resistance here to ground, what's my meter going to read now? We don't know what it's going to read, but it's going to be less than 7,200 volts. Okay? It's that same principle I talked about the line further we get away from the substation, the resistance in the line, how the voltage lowers, how it drops. Okay. 7,200 volts the same to ground. We still have the resistance in the line, but now we got a bond from here to here. So what's the voltage going to read there? It's going to read 0. So we're going to show what the actual voltage is here in just a second, but you can see the difference in that bond that we put around there, what it did to us. Kilo ohm would be us, 2 ohms down here, 4,048 volts. The actual meter across there, 21.5, 24 milliamps. What's our buffer zone? 50 and 50. So we are well below the 50 volts penetrate our skin. I know that most of you linemen are out there. It's probably going to take more than 50 volts to penetrate your skin. So what about your wife? What about a baby? You know, you can see the differences in our skin, the resistance. But if we can stay below that 50 volt buffer zone, that's where we want to be. So this right here is kind of the meat of my whole presentation that I want to talk about today. All of that stuff that we're talking about before is theory. You know, we go through, we test, we try to develop. We have a working theory that we have gone through and we've proven. But things happen and change. Sometimes theories change a little bit. They improve, they get better because we learn something all the time. This is an actual tailgate that happened. You can see they went through, filled out their tailgate, they talked about things, filled out the tailgate. Last part of the tailgate, they went through, I crossed out the names that was there that was signed. Okay, so this happened in September. A fish hatchery was single-phased. Okay, they're out of power. They called the power company. They said, we don't have power. All our stuff isn't working. Would you come and check it out? So a lineman was sent out. There was a crew foreman, a lineman, and a part-time help. This kid was thinking about going to Northwest Lineman College and becoming a lineman. What influences your decisions that you make? Do you have your boss show up on things? Does that influence the way you do your job? Do you have somebody that's watching that is going to go on like that young gentleman that was thinking about being a lineman? Did that influence what happened? I don't know. Hopefully it did not. Hopefully that we do things because we want to go home. Hopefully we live our lives, we do our jobs in a way that we protect everyone around us, and we do it in a way that we're safe, that we can go home and we can ride a horse. We can go watch a baseball game. We can go do everything that we love to do when we get home. So, back to my story. You can see there was a bear trap that was left on this line. You can see this wire that's hanging down from the bottom of that shoe. It's hanging down approximately 8 inches from the bottom of that shoe. So here comes the line crew. They come up, they patrol the line, and they look up, and they have a stinger that is going to, you can see the phase, you can see the line that's going this way, and now we have a tap that's going this way to the fish hatchery, and they had a stinger that was burned off. So they had a good tailgate, and they decided what they needed to do. They decided what they needed to do, how they needed to do it. So the first thing they do is they call dispatch. Would you put this line on non-reclose? Would you put this on one shot? Okay, so we got the line on non-reclose. Okay, and now the next thing, they go through and they have everything prepared to climb the pole. The line foreman climbs the pole. Okay, he climbs up. First thing he does is he hangs his Equipotential bracket. Did he hang that because he had influence here watching him? Like I said, hopefully not. But that day, he did what he was supposed to. He had a wire brush on his outfit. He cleaned his connections like we're asked to do. He hangs his bracket. He puts his ground chain to the neutral. Okay, he's already dropped the wires off the phases. So now he's going to ground this line going this way to the fish hatchery. So he puts up one, makes a connection. He wiggles it back and forth, so he makes a good connection. So it penetrates through, clamps that down tight. He puts up the second one, does the same thing. Now the third one, when he went to put it up, he brought it up and he had to go over across, so he had the ground chain laying across his shoulder to reach over the top. As he went to reach over the top, he pushed that straight. That belly and that ground chain flipped up into the bottom of that phase and made contact with that 6-inch tail that's hanging out of that shoe. The recloser did exactly what it was supposed to do. Operated about 6 to 8 cycles, whatever. All it had was just that. That ground chain was laying across his shoulder. Lineman on the ground hollers up, "Holy crap, are you okay?" And that lineman looked around for a second. He said, "I never felt a thing." He said, "This crap really works." So I want to ask you again, what influences your decisions? What causes you to do the things you do? Is it knowing that your wife would be mad if you burn off an arm or whatever? Or what causes you to do those things? I want you to think about it, and then I'm going to ask that same question to you at the end. I don't know what your company does, but I do know what this company right here does today. Every single crew uses their Equipotential grounding every single time because of what happened right here. I don't know what's going to happen 6 weeks from today. I don't know what's going to happen a year from today. But I do know today, every single crew is grounding like they have been trained and taught. What causes you to change? Do you have to have skin in the game to actually see something to change? To make things better, to make things safer? I want you to think about that. Now I'm going to talk about one more incident. This occurred in Texas a few years ago. Contractor. They're in the backyard. They have bracket grounding on each side. The line has been de-energized. They have their bracket grounds. They have linemen that are working in. They have their own grounds that they're putting up the pole. Okay, and they're just by themselves. Nobody's around. So as they go up, they have their grounds hooked on a hand line. They just pull everything up. They ground as they go. They get the project done. They come down, then they go to the next structure. 2 span apart. This lineman over here grounded just exactly like this. He used his equipotential bracket. Lineman 2 span away grounded like this. Okay, he just put his working grounds up and not his personal protective grounds up. They're up working on the line. This lineman just gets finished, he comes down, he gets a call on his cell phone. Stay off that line, it's become energized. There was an outfit that had hit a pole. The pole had fallen into the phase that the line that they was working on, energized that line. That lineman says, wasn't energized, I just barely come off of it. He said, yes it is. We can't get a hold of your pole buddy. He said, well, he's only 2 span away. I'll walk down there and I'll talk to him. So he went down there to talk to him. He's laying upside down, electrocuted and killed. Was that the difference in life and death? According to this gentleman right here that tells his own personal story, that's why he is still alive today. What influences your decisions that you make? Puget Sound and Power and Light, they did some studies. Okay, so they actually set up working brackets. You can see the brackets, the working grounds, and the personal protective. Okay, you can see these numbers just with working grounds with their test facilities, how they was set up, which we all understand and know that is a controlled environment. But you can see this at 52.5, 58, they are over our buffer zone. They're over that 50 volts. You can see just with bracket groundings, we're up here at 103 volts, 94 milliamps. We're at that no return. Now look here at our personal protective grounds. Every test that they have done here, there's 3 tests here. You can see one at 13 volts, 10 volts, 8 volts, 14 milliamp, 11 milliamp, 10 milliamp. That study was done in 1988. Why isn't more of us using Equipotential? Food for thought. So they talk about how far away. So if I have my bracket set up here, see my personal protection. Can I work a span away? Can I set up here? Can I work here? That's kind of an engineer question. I don't know how much resistance you have in your line here, because we know that if we have resistance, it's going to raise the voltage. But the way that they've understood the test they have, if they're working on one phase away from it, they're going to be okay. These 2 up here that's maybe not grounded, it's going to be higher, but it's still probably not high enough to be deadly. But that's an engineer question. That's somebody that understands and knows your system, how much resistance, whatever you have on your system, that can actually tell you that. I do know, with all the testing, that you're safe here. Probably here is probably good enough for you. We know further than that, now things change. So, I'm just going to talk about induction for just a little bit. So, if I'm using personal protective, are the induction risks controls different than the risk controls for unintentional energizing? Is there any difference, or are they the same? They're the same, aren't they? Okay. Whether it's induction, so we have two transmission lines set up here. We're energized here, we're energized here. So what's it going to do to our line here that's de-energized and grounded? You can still see that influence, that electrical influence, that induction on that line. A lot of factors go in place on induction, but you can see how that's influenced there. So if we have voltage, capacitive coupling, or we have magnetic coupling, and we put a ground on, we're going to collapse the voltage. The voltage is going to collapse. Okay, so now we have two sets of grounds here on this magnetic, on this inductive line here. One thing we always want to remember, and like I say, it's something that I lacked probably when I was a lineman. We're going to have a continuous flow of current here on this, and we're going to develop a circulating current. Something to really think about. Okay, so here's the truth. For every ohm of resistance that we put into our protective system rises the voltage across our body in an incident. But if we can control that voltage, the current does not matter. So when you work out on a line, how do you ground your line you work? Do you just ground one phase on a three-phase line? Or do you ground all of them? OSHA says that you will ground all three phases, okay? And in grounding all three phases, we ensure faster operation of that recloser. Short-circuiting all three phases will ensure faster clearing and lower the current through the grounding cable connecting the de-energized line to ground, thereby lowering the voltage across that cable. Okay, you can kind of see here whether it's Y or delta. At the 120 offset, grounding change to eliminate that resistance, creating high flow between the phases at the same time, eliminating ground path flow. So it operates. Here's just another kind of picture to kind of help us see how that works, but it's exactly the same as what we just talked about. So ground change between phases bypass that impedance and creates a rush of current which trips that circuit. What is your cardinal rules for grounding? Every single company has their own set of rules. At least you better have, okay? Here's a set that we put together here at ISPC. Okay? Number one, we're going to mechanically and we're going to physically disconnect the line. Number two, we're going to test the presence for voltage. Everybody's got buzz testers. Everybody has their testers. They need to use them every single time. Now I'm going to hang my Equipotential bracket. And I'm going to connect it to the neutral. I'm going to make sure that I connect to the ground source first. That's my first connection. Make sure I do the ground source first. And I'm going to connect to the closest phase, and I'm going to use a hot stick. And then I'm going to connect to all of them. Then once I get finished, I'm going to disconnect in the reverse order. Always use a hot stick. Okay? Never handle an unconnected end of a connected ground cable. Always use a hot stick. Here's an out of order case study. Okay? What this is a transmission line. This is a snub pole on both sides. They have the wire snubbed off here. And now they're going to splice the wire and then they'll let it back up. So they have this grounded and they have a ground mat that they're using. So they're grounded here, everything's good. So they pull the wire together and they crimp the sleeve. So now I can take this off, I can take my bond off because I don't need it anymore, because now my wire's solid. Okay? And now they take off this hoist on this side. What happened? They took the ground off, but before they took their hoist off. There was a journeyman lineman over here. He was an older hand. He was sitting here. There was an apprentice on here. And now he's reaching up here to take this off, and he could hear that hoist rattling down through that chain. And he understood that sound of that power, them connections running down through that chain. And as this apprentice was reaching up to take that off, he ran over there and stopped him. He hollered at him, he stopped him. So they got curious. They thought, They put an amp meter and a voltmeter on that hoist, on that chain right there. There was 42 amps and 844 volts that he was going to take off and to make that path to ground. There's a good likelihood that he would have not gone home that night. Thank goodness for that lineman that was aware of the situation, of that difference, that sound. What of your observers that you send out? Are they qualified to be watching what's going on? Are they doing paperwork? Are they engaged in conversation? How important is a safety watch? Well, today, that day, that was very important to that apprentice lineman. Made the difference in life and death to that apprentice lineman that day. Here's another cardinal rules from grounding on a different type of structure. So I'm just going to ask you again, what is your cardinal rules from grounding? Do you do the same thing every single day? Every single time? Do you take them off the same way every single time? What is your cardinal rules for grounding? What kind of grounds do you use? We talked about that earlier. Do you use grounds that are made for a specific job? Normally we're going to have distribution grounds. Depending on what our system needs. And we're going to have them tested in the same length. We understand, we know what we have in our truck? Or do we have a set of grounds, one size fits all, whether it's transmission, rolled up here to work on distribution? What's going to happen to that cable right there if that becomes hot? That becomes energized.
Maybe you remember the, you ready? Okay, 4, 3, 2, 1.
Yeah! Everybody look at the smoke. I'm going to talk to you about that in a minute.
Did everybody see this clamp right here? Watch what happens to this clamp. Okay, they was up to Bonneville and they're doing a test. There is a incident prevention that was up there, and so they have all these students, and they happen to have Danny Rains, they happen to have Jim Vaughn, Mac Turner, and I'm not sure who all else was there, but they're sitting there watching. They had, how many of you on your system maybe have ground chains that are too small and you need to put another set of ground chains up to have the capacity that you need? What happened up there that day is those guys were standing there visiting, watching that demonstration, and they watched, and one turned to the other and said, "Did you just see what I seen?" Everybody's shaking their head wondering what's going on. So when the students all left, they went to those guys and they said, "Would you do that again for us?" I said, "Sure." So they set up, did it again, happened exactly the same way. They said, "That shouldn't happen that way. What's going on here? Why is that ground chain coming to the other one?" You can see the difference, how far they had it apart. Well, they got doing some more studying, and they found out if they was 10 inches away, they lost 90% of what they was trying to accomplish. If they was only an inch away, the closer they got, they was an inch away, they only lost 10%. So you can see the difference if you happen to have to put a parallel set of ground chains up. You can see the difference from 10 inches losing 90% than if it's right close together. Very best thing is to have one set of ground chains that is adequate for what you're doing. And I think probably nowadays we're to that point that we all do. So how do you put up your ground chains? Do you set them up to where you have a balanced ground chain? You send them up to where it's imbalanced. Makes a big difference on the reaction. Okay? Also, this balanced, now you're going to have a whole lot of whipping on both sides. So preferred less. Okay, parallel 2-watt. Here's another test right here for us. Here's a single phase to phase to ground. Then here's parallel twisted. You can see the violent reaction anytime you have a fault on those grounds. So, for recommendations, how do I make my grounding for personal protection work? I need to understand where that current can flow. I need to understand all of the paths, all of the current paths that the current can flow. Are there additional paths? What's available there? How do I bond in? How do I electrically isolate myself? And I have to understand what those limitations are. I might have to do a combination of different things, but I have to understand those paths. I have to understand what my limitations are, okay, of what I choose to do. Okay, I want to talk now a little bit about some case studies, kind of maybe get you thinking about things that you do and you work and how they can affect maybe how you do things. There was this contractors, they're going through, and I'm sure most of you seen, they used to have wire that was run across here for this bed ridge across the top. And over time, they break and pretty soon they're gone all the way across there. So they was putting up new rails across the top. So they'd been doing it day after day after day after day. Well, this particular structure, they went up, they hung the bed rail up on top, they connected to this side. So you can see their grounds. They had their grounds up. Okay, what have we been talking about? Circulating current. Okay, so we understand that anytime we have a grounded conductor, anytime we have induction, we're going to have current flowing every single time. So we do understand that. So you can see the path. Well, he went up here, made this side up, went over here, went up here to make this side up as he grabbed the pull bond and reached over to put it on the static. He was electrocuted, and because of an AED in a pickup and a well-trained crew, they was able to save that gentleman's life. You know, we did everything they thought they were supposed to do. They come here, they have their bracket grounding on the pole. They did what they're taught. Didn't even think about the circulating current. I probably wouldn't have either. Like I say, years ago, it's something that maybe wasn't taught to me enough. Available path. I don't know how many of you are getting to put in the OPGW, the static, but they're pulling in some OPGW line here. And you can see they come here and they're coming down this pole. Well, this line crew was, you can see where the brackets on the pole as they're going down, they're connecting them too. Well, this line crew was connected, had their bucket connected to this bracket. I'm not sure where it is, I can't see it. I'll be able to see it here in just a minute. And as they brought that down, they had to take the bond off their truck so they could connect the OPGW to this bracket. They're in a bare hand bucket. So they're in a metal bucket. And I'll show you the picture of that in just a second. Well, they took the bond off. Kind of see where, it's kind of hard to see right there. Now you can see it right there. They took their bond off here. They swung out. they swung back over here and they leaned up against this shiv right here. The lineman reached over to grab that to pull that down to bond and was electrocuted and killed because of the static and the truck not bonded. Okay, you can see where he was set and he pushed up against the structure. Here's the bare hand bucket. You can see this metal bucket here that they just pushed over. So when he reached over and grabbed it, now he made the path to ground. We always need to be paying attention to different paths. I don't know if anybody's ever seen a structure like this before. I hadn't before. Double circuit line coming in, went off with a single line coming off the other direction. Okay, that's what the structure looks like. Okay, you can see the double bundle coming in here and single going off this side. So they had the steel structures, insulators, and they had the anchors coming off the back side. These anchors was set at about a foot apart. As they come down off, there was about a foot difference between. So you can see right here, there was a lineman walking between these two down guys, came in contact with this one and this one right here, and was electrocuted and killed because of the differences in potential from one to the other. They tested the voltage on there and there was 300 volts between those two guys. 16.9 amps. How many of you work in substations? His substation crew right here had been working in a substation. This is just a steel lift. Goes up here. They have their lift grounded to the ground grid. They're grounded over here to the ground grid on this side. Been doing the same thing for 20 years. This particular day, they grounded their truck. Everything grounded. Now he went up here to come here. Now I have two differences in potential. I don't know if anybody here has built a ground grid, substation ground grid before. I do know that I was involved with it once. Let me tell you a little bit about my experience. So we go and we dig the trenches. Every 4 feet we have that 4-aught wire, goes here and it crosses here, and now we're told that we have to weld those together. So we're brought out this CAD weld and they say, here, go weld these together. And so we look at that and we go, okay, just like we do. What kind of training do we have? Here. Go take care of it. So we look at it and we say, okay. So we go out in the substation. First thing we do is we get a couple of short pieces of wire and we pour that powder in and we get everything right. We light it, it goes down, it melts. We pull up, we look at it, we go, heck, that looks pretty good. I can do this. So we go to one hole, we do the same thing, pour the powder in, light it, look at it. Oh, that looks really good. We go over here to the next one. We light it and do it and we look at it and we go, oh heck, that looks like that's half burned off to me. Must still be good. So we cover it up and go on. Anybody else had any situations like that? How do we know what this ground grid was? How do we know what this soil condition is? Does anybody test their grids in their sub? How do you know that it's good if you do not? So, two differences in potential. Difference between here and here, he reaches over and comes in contact here with this potential and is electrocuted and killed. Why? What happened here? Circulating current again. How can we prevent the circulating current? What do we have to do? Have to put a bond on. If he would have put a bond on here, we just eliminated the hazard. What else could we do? Do we have to have our lift and our substation grounded? If we do, is there a better place that we can ground it so we're at the same potential? That we eliminate all of this resistance, this difference? Can we ground it here? Or can we eliminate it and have it grounded this way? Why are we grounding? Why do we ground our trucks? Why do we ground? So if we're inside a substation, how are we going to open the substation? What are we grounding? What are we accomplishing? It's just things that we need to think about when we ground, when we do. The current pass, what are we actually accomplishing? This is what we want to accomplish for sure, is we want to be at the same potential. Everything that I'm working on, I want to be at the same potential. There's another case study. We like the ones that don't have a fatality. They're working here in the substation and they're putting a bus across here. Well, this lineman's up here working on this line. As you can see, this bus that they're putting up here, anyway, they ended up dropping this one. You can see what the induction, that actually welded to that structure right there. See, it just let a burn on his finger. Those are the little incidents, if they happen, that we like to talk about. We don't like to talk about those fatalities. How do we need to ground those structures? That's something that you need to think about. You need to, before that time, you need to take just a little bit more time as you're going through and look at those paths. Is there circulating current? What can I do? How can I bond in to stay at that same potential? Easy job here. Okay? Job is they're taking this structure out. You can see it's going to fall off here pretty soon. You see this? They had that little piece of cover up there for reference. The only thing that's sitting there is just so they can see that phase as they're cutting that down. Well, they get all this cut down and they look up there and they see that piece of gut that they left up there on the line. So they head right back up in the truck. They go up to get this off. The lineman just goes up to get that off, reaches up there, grabs a hold of it and pulls it off. Another thankful for AED and a trained crew. He was electrocuted when he made contact with that grounded line because of the induction. Okay? He had a grounded crane lift. So we had a great path to ground. You can see the resistance, the guy in the crane and the outfit. He was grounded, great path to ground. When he reached up, touch that to pull that off. Electrocuted him, and like I say, thanks to a AED and a good crew, saved this gentleman's life. So, how could he work on that safely? What should he have done? You know, as we're getting our job done, we go through our jobs and something changes. It's not all cut and dry every single time. Something changed. What changed? They forgot that piece of cover-up that got up there. They forgot that. The whole project changed for them at that moment right there. So, I'm going to come back to that slide. So, here's a bare hand principle. So if they would have went up and they would have bonded to that, then he could reach over and grabbed it. Or used a stick or whatever to get it off. But didn't even think about it. You know, he just went up, I'll just go up and get that off and we'll be good. Bare hand principle. So if I'm up working on a line, and I put a jumper there, everything that is in that area is all the same potential. Normally what I'm going to do is, if I'm going to bare hand or whatever, I'll have one on one side and one on the other in case one comes off, then I'm still at that same potential. If I happen to move and one falls, here. But you can see, just like a bird on the wire, if I go up, because of my boom, my insulated boom, I go up, bond on to the line, I'm at the same potential. So, back to this slide that I had just before. You can see that they went up and they put a splice on here. You can see my Equipotential bracket here and here. We're up here, you can see my 34.5, so my static buildup. So he was wondering why in the heck he was getting shocked, because he's grounded like we're supposed to, but now he's out here isolated. He's out here in the middle. He's at a different potential out there in the middle than he would be if he was on the structure. I'm sure you can all see that. So, how can we protect? What can we do to protect around a vehicle? Okay? OSHA says, thou shalt, unless an employer can demonstrate the methods in use to protect each employee, the measures you shall include all of the following techniques. Using the best available ground to minimize the time the line remains energized. The bonding equipment together to minimize potential differences. Providing ground mats to extend areas of Equipotential, and employing insulating guards against any remaining hazards and potentials. So, what is the best available ground? What does OSHA say the best available ground is? Is it a ground rod driven in the sand? What is the best available ground? OSHA says the neutral. The neutral is the best available ground. So if we ground our trucks, we need to ground them to the system neutral. Bonding equipment together to minimize the potential differences. So how do we bond them together? What do we do to bond them to make sure they're all the same potential? Is this how we do it? Every piece of equipment's tied, or are there different ways? Are there maybe better ways? Providing ground mats to extend the areas of Equipotential. See this big ground mat that they've got set up here? So if it becomes energized, now everything inside of that fence, that barricade that they have set up there, is all at the same voltage. Employing insulating protective equipment or barricades to guard against any remaining hazards. We all need a good guard to make sure nobody enters in to the zone. You can see their barricade that they have around the outside. You can see their mat that they have here set up. So they're doing everything that they can to minimize that hazard on number 4. I like the guard dog myself. So, I'm grounded up to the system neutral. What else do I have to do to make sure that that is a secure area? Or am I good right there? Is everything good since I've gone up here and I've connected there? What about the touch potential? Do I have to worry about that? What can I do to make that safe? Do I have to put some kind of a mat up, something to make that safe? Or do I barricade it to make sure that nobody can get into that zone anyway? What's those placards on this truck say? It's on every single truck. Tells us do not touch this truck. If that's working on that zone, it tells me to stay away from that truck. So, here's my truck. I've set up a mat. What happens if it becomes energized? I'm all energized at the same potential. Okay? Where's all the hazards? What hazards are there besides that when that becomes energized? You can see now my 10 foot that we've talked about starts right here instead of here. It starts right here. Now I have my 10 feet out here, the same as I have on these areas. Okay? What else do I need to do to make that safe? Is that safe for me to approach that truck? Or do I have to have something else to get onto that mat to make it safe? To me, the best and the easiest way is, if I have to get on that truck, those linemen have to come out of that zone. If they come out of that zone, now I can enter the truck. Even if I ground the truck, I still have to have some kind of a barricade around to protect the public and to protect the rest of the employees. Food for thought. How many of you have went up to a truck to get a piece of hardware, some kind of tool, some cover up off that truck when they've actually been up in working on the zone in your career? If you would have had a barricade, would that have changed the thought? Would you run into, oh, I can't get on that truck right now? As to where if there's nothing there and you're thinking about that big bull that you've seen that morning on the way to work, or thinking about going fishing or whatever, and you need something, do we think about that? Food for thought. Myself, I've never been an advocate for grounding trucks, but I do believe in barricading, because If you ground your trucks, you still got to barricade it. You still got to have somebody there to making sure that everybody stays out of that zone. You still have to barricade some way. And so that's me personally. We just barricaded and stayed the heck away from it. Brand spanking new digger. This digger was put on the line Monday morning. This is Thursday. 4 days. They are taking a recloser. They're replacing a recloser that's up on the structure. So they have a good tailgate and they decide exactly what they're going to do. So this gentleman was supposed to lift that recloser up. He was supposed to swing it around and set it on the ground. Everything worked good. So he picks it off, he lifts it, he swings it over to set it on the ground, and then he thinks, why in the heck am I setting that on the ground? Why don't I just set it right here on the back of this truck? So we don't have to lift it up and put it in the truck. Mental breakdown. He forgot the hazards. He forgot what he was doing. So he lifted that up to swing it in, to set it in the truck, and made contact with the phase above him. So he was just going to swing it over and set it down instead of he just brought it up and come in contact. This truck burned for 53 seconds before the recloser opened. See where the trucks was set up? Contact point on the digger. You see, we talked about that 10-foot circle. You can see how that burns. You can see the color of the soil. That tire blew off about 5 minutes after power had gone off. It had just sit there about 5 minutes, and then all of a sudden they heard a boom, and that tire blew off that rim right there. Here's the ground chain. You can see the burn places on it. 1 month ago in Florida, I don't know if any of you heard this or not. This just happened just 5 weeks ago.
A Florida Power and Light worker electrocuted right on the job. The sparks also causing an FPL truck to catch on fire.
NBC6's Willard Shepard is following the latest developments and joins us live from Southwest Miami-Dade with more. Willard.
Well, Juwan, just a terrible tragedy here that unfolded here behind me in Southwest Miami-Dade. A person just walking by with his two dogs, saying how much this has impacted this entire community. A lot of people here actually saw this unfold, as you'll see in the video we're about to play for you. And this entire community is sending out their thoughts and prayers to the family of this worker who was in their neighborhood trying to keep their power on. This was the dramatic scene in Southwest Miami-Dade County. On Wednesday, an FP&L truck billowing smoke, and in the background, workers coming to the aid of the man who was electrocuted here. Miami-Dade police told us that between 10 and 11 a.m., a man who was working on the power lines was electrocuted. One man who lives on this block told us what he saw.
I seen the guy on the top of the machine doing his job. He fell down, he caught on fire. And he caught on fire, he started shaking, he caught on fire again. And then the workers, the guys that work with him, they ran over there to help him out.
Police spokesman Louis Sierra says the worker's truck did touch the power line.
A power line did come in contact with this truck, and the truck did catch on fire.
But Sierra says beyond that, they don't know exactly why the worker, who was in his 30s, was electrocuted.
We do know that electricians are routinely inspecting and checking lines. The circumstances of how this happened, we do not know.
The streetlights were out, and so was the power for several blocks.
I was dying of the heat, and the fan was off, so when I came outside, I realized that there was helicopters flying everywhere, and there was just essentially no power. All the neighbors were outside.
Neighbor Julius Hall looked at the scene not far from his home and commented on how the morning that started out just fine, seemingly like any other day, keeping the power going to homes, took such a tragic turn.
He went to work to provide for his family, and he's not going home. And that's very sad. So with the power being out, is a minor inconvenience for what that guy's family is finna go through.
And that's really the feeling of many in this neighborhood. We see some of the homes here behind us now. It doesn't look like they have any power yet either. But as Mr. Hall said right there, that's insignificant compared to the loss of life here. This man was rushed to the Jackson Hospital system. However, doctors were unable to save him. We're live tonight in Northwest Miami-Dade. Willard Shepard, NBC6.
We need to make sure that we get out doing those jobs and stuff. We have our mind focused. We understand the situation. We understand the hazards. Okay, let's talk just a little bit more about grounding trucks, and then I'm going to kind of wind up and talk about a few more things. So, 2 trucks here. You can see, according to policy here, this truck is grounded here. This truck is grounded here. Okay, so where's the hazards? Where is the hazard on this structure? It's right here, isn't it? It's between those 2 trucks, just like that anchors that was in the ground. Those 2 guy wires coming down. Well, that same thing is here. I have a difference in potential in this truck and this truck. 2 different potentials. So if I put a bond between them, now I'm at the same potential. But what have I created here? Grounded, bond, grounded. What have I created? I've created a circulating current. So how can I eliminate that? What can I do to eliminate it? So I've taken that one off. Am I still grounded to the neutral? Do I have a bond? So am I at the same potential here? So I'm still safe for all my employees on the ground? There was a crew that was set up just exactly like that right there. Safety guys, you know, we're supposed to know everything, know-it-alls. He pulls up on the job and he sees this truck is not grounded here. Our safety rules says that we have to have this truck grounded. You need to put a ground there. So he made them ground that truck, not realizing the hazard that he just created for the workers. So we as safety professionals need to understand and need to know before we come and tell somebody something. So a couple of things that I want to leave you with today. I know that we're getting close to the end of our time. I guess the very most important thing that I want to leave you with today is what influences your decision. Why do you do the things that you do? Do you do it because of peer pressure? Do you do it because the foreman tells you that you need to do it? Do you do it because that's just you? That's just what you want to do. You want to be the best you can be. You want to be the safest you could be. Do you do it because you have a part-time help that's thinking about going to line school, what influences the way that you work, the things that you do? Do you have to have skin in the game? Does something happen or have to happen that causes you to change the way that you think? You know, it's hard in our industry because of those influences that we have. We do things because of the influences, to the most part. We do them because we've done it that way for 30 years. We do it because we have training that comes in and tells us that we need to do something this way because of this reason. I don't know what it is. I don't know why. You know, thinking back on my career, was I lucky? I know that I was in lots of situations. Why do we do those things? How big's your family? Let me tell you a little bit about that lineman that actually did what he was supposed to that day, that I told that story earlier. You know, the first thing out of his mouth was, "Is this crap really works?" When he got home that night, he went and watched his son play a baseball game. He went and watched his son play a baseball game because of the decision that he made that morning. If he would have chose, we all have that choice. We can all choose how we want to work. If we want to work safely, if we want to work reckless, we all have that choice. We can all choose how we want to work, how reckless, how careful, whatever. We can make that choice. But that morning, he chose to do what he'd been taught. That night, he went home and he watched his son play a baseball game. Why do we do the things that we do? I hope we do them for the right reasons. Thanks for inviting me here today. I've enjoyed being here. Hopefully you've been able to pick something out of this presentation, and if it's only one thing, then I've accomplished everything that I can today. I really, honestly, truly believe if I can just reach one person, I've done everything that I can do. But if that happens to grow and he reaches somebody else, or I happen to reach more people, we just make our industry better and better and better, and we become safer. We got to quit killing people. Just like this accident that happened 5 weeks ago. Maybe he was supposed to go to a baseball game that night. I have no idea what he had, but we need to be careful, and we need to be our brother's keeper. We need to watch out for our pull buddies. It affects you. When I was just starting out in the industry, I had a pull buddy that I worked with almost every day. And I was in a different area than where I grew up. I got to move home the first day of March. The 26th day of March at 3:30 in the afternoon, my pull buddy that I worked with every day, or almost every day, for the past year, came in contact with a lineman and was electrocuted and killed. I can remember where I was driving down the road. When that Mayday call come across the road, I can remember pulling right off to the side of the road, and I sit there for probably an hour and a half listening to every single word that came across that radio. Back in those days, we didn't have the cell phones. It was all radio communication. And that communication was poor at times back then. But I can remember the effect that that had on my life at that point in time. I can remember sitting there holding on every single word that was said, hoping and praying for the best. He was married. He had about a 10-month-old little son. His wife never remarried, and I've lost contact with their family. They ended up moving from the location they was at. So I don't know how the rest of the story ended up being, but I do know the effect that it had on my life, other lives that was around him. So I just want to again remind you about looking at the different ways that the different paths, the different ways, the different feeds. Know the system. Know the very best way that you can protect you and yourself. Because we truly work so we can go home and we can enjoy life. That's all that I have for you today. So thank you, and thank you for the time.